Good morning, students. As you know, my name is Subodh Pandey, and you are floating with me in the world of physics. We are going through a chapter, and the chapter name is your surface tension. In that chapter, we have to discuss about the viscosity, and that I have already completed for you. Okay, now we have to discuss a new topic in that particular chapter, and the topic name is Stokes law. Okay, so what is Stokes law? As you can see that if we talk about a solid body, okay, so if we have a solid body and that body is flowing through a fluid, then we can conclude that as we know that every fluid has a property, and the property is called viscosity. Okay, so if we have a fluid has a property of viscosity. Viscosity is we can say that it is nothing but a friction. Okay, there are different layers of the fluids. Different layers are in relative motion, and now a solid body is flowing through that fluid. Then what will happen? Basically, we can assume, we can say that let's suppose that this be your solid body, that is in the shape of a sphere like a ball. Okay, and the ball is moving with speed v. Okay, now what if let's suppose each and everywhere around the ball there is air molecules, the layers of the air. Okay, so let be this is the a layer of the air, like this way. Okay, you have to assume this thing like this way. Okay, so you will see these are the layers of the air in the atmosphere. Okay, like this way. Good. Now what? As you can see here that the ball, whatever is moving, it has few layers in contact. So if we see these portions, means if we talk about this layer and if we talk about this one, these two layers are in contact with the solid ball or solid body. Okay, and if we compare these layers and these layers with the intermediate layers, then we can easily say that these layers, which are the outer edge, which are at the outer edge, they are not in the contact with the solid body. Okay, what does it mean? It means suppose we have a layer like this way. Okay, we have another layer like this way, we have one more layer like this way. Okay, so there are several layers, and let's suppose that this layer be first layer, this be your second layer, this be your third layer. As I have shown here, this is first layer, this is second layer, this is third layer, like this way. And the third layer is you can simply say that it is in contact with the ball. So this is your solid body and the third layer is in contact. Okay, now as I have told you that the speed of that spherical body or the ball is v. It means the layer which is in contact with the ball has nearly approx, we can say, the same speed. okay, as of the spherical ball, because the third layer is directly in the contact with the ball. Okay, now what? Because the second layer and the third layer, these two layers has a friction force, and that friction force I have named that viscous force. Okay, so here there is a viscous force. What does it mean? It means let be the second layer has velocity v dash, and that is obvious thing that v dash must be less than v, and the process continues. When we reach to the first layer, then let be the speed becomes v double dash. So if we compare these two layers, the second layer and the first layer, then we can easily say that v double dash must be less than v dash, and this is due to the viscous force. In short, we have a result. What result we have? That due to viscosity, the speed, what speed transfers through the layers, that decreases. Okay, means the first layer has speed v double dash, second layer has v dash, third layer has v, and this is a decreasing order. Now what? As we know that each and everything wants to maintain its inertia, it means they tries to oppose the relative motion, and if they tries to oppose the relative motion, then what will happen? Then the first layer opposed to the second layer opposed to the third layer, and third layer opposed to the speed of that spherical body, and as a result finally we see that that body comes at rest finally. And why it comes at rest? The reason is quite simple: due to the viscous force which acts amongst the layer, and this is a dragging force. Okay, so we can simply observe this phenomena in the nature, and finally we have some unique results. What are the unique results here? So first result, what we get? The first result what we get, number one, that is whatever the dragging force appears, that depends on the velocity itself. Means if there is a larger velocity, higher velocity by which the spherical body is thrown, then we can see easily that the dragging force must be in the same order. Means it will be, we can say that it will be higher in magnitude, but if we slightly drop anything, we slightly push the ball in the fluid, then we can simply say that the balancing viscous force must be the lighter in its magnitude. Okay. Now the second observation, what we see that the viscous force here F, that depends on the coefficient of viscosity, and as I have already told you that the coefficient of viscosity is nothing but the fluid itself. It means viscous force or the dragging force depends on the fluid. It is obvious, you know very well that if we have different types of fluid, then if suppose there are two fluids, first is water, second is honey, then honey is more viscous which compared to the water. So it means the viscous force will depend on the fluid itself. Okay. Now the third result we have also that the viscous force or dragging force depends on the shape and size of the body. So here the body is taken as spherical shape, so it depends on R. So R, this one represent the shape and size. Shape and size of the body of the object. So I hope that this thing is clear to all of you. Now these observations we have can be easily give a expression, and how we can calculate that expression. That expression can be easily calculated by using dimensional analysis, what you have gone through in your class 11th. So what we have to do, firstly we have to write that f depends upon eta and then r and then v, and the power is taken as a, b and c, and it is maybe if we remove that proportionality sign, then the constant will be k, let's suppose, and eta times a, r times b and v times c. Let be this equation number first. I hope that up to here each and everything is clear. So basically Stokes studied about the dragging force when a body passes through any fluid. So this thing is very useful to remember. And then what we have to do, firstly we have to write the dimensions of the both sides. So what is the dimension of viscous force? Viscous force is nothing but it is a force itself. So dimension will be m into a, and a will be lt minus 1. So this is the dimension of force. Here k is the constant, so dimension will be no dimension we can say, and it will be dimensionless. Eta is your viscosity, and the dimension of the viscosity we have already explained to you in your previous lectures. Okay, so here you can see that I have show you that how we can calculate the dimension of the coefficient of viscosity in your previous lecture, and the dimension what we get, that is ml minus 1 t minus 1. So we will directly use here, the dimension will be ml minus 1 t minus 1. Okay, so this is the dimension of the coefficient of viscosity. Now we have r is basically the radius, or we can say that length, so l, and the power will be, and we have v speed, so speed lt minus 1 and the power will be c. Now what we have to do, we have to rearrange these things. So here we can write ml minus 1 mlt minus 2. Okay, and this it will be minus 2, m into a, so acceleration, and here you can see that m to the power a, and there is no m, so m to the power a, so m to the power a, then come to the l, here l to the power minus 1 and a, so minus a, l to the power b and l to the power c, so minus a plus b plus c, so minus a plus b plus c, and now t, so here you can see t to the power minus a, t to the power minus c, so minus a minus c, so minus a minus c, and now it's time to compare. So we will compare, and on comparing what we see, on comparing we get that the value of a, that is 1, the value of minus a plus b plus c, and that is also 1, and minus a minus c, that is minus 2. Okay, so let be this is your here is this equation 1. Okay, so let be this is equation number a, b and c. Now what we have to do, we have to calculate the value of a, b and c with the help of these three equations a, b, c. So when we put the value of a in equation number c, then what we get? we get minus 1 minus c, that is minus 2, or we can write 1 plus c, that will be 2, or c equal 1. So this is the value of c, this is the value of a. And when we put the value of a and c in equation number b in this equation, then what will we get? We can write that firstly we have equation minus a plus b plus c. So minus a plus b plus c, and that is equal to 1. So this be your 1. A is 1, c is 1. So this 1 e and c is 1. This is 1. So 1 and 1 cancel out, and we have b equal 1. So finally we get the value of a, b and c. So now what we have to put the values of a, b and c in equation 1. So from equation 1 we have the f equal k times eta to the power 1, r to the power 1 and v to the power 1. Okay, by experiment. There are several experiments it performed, and after that the value of constant k 6 pi. So finally we get the result as 6 pi eta r v. So I hope and I believe that up to here each and everything is now clear to all of you. Now what you have to do? You have to try to solve this derivation by yourself. Okay, then what? Once you have solved it, then you can better understand what I am trying to explain. Okay, so this is your final result, and the result is f equal 6 pi eta rv, and this is your viscous force, and this formula is derived by Stokes. So that's why it is called the Stokes law. So this is the heading, Stokes law, and this is the final your formula for the Stokes law. So I hope that up to here each and everything is clear now. Now we will come to a numerical for you. See, this is your question. An air bubble of diameter 2 mm rises steadily through a solution of density 1750 kg meter inverse cube at the rate of 0.35 centimeters second inverse. Calculate the coefficient of viscosity. The density of air is negligible. It is given to you. How will we solve this question? Now one thing, if you have noticed that the air bubble rises through a solution. It means let be this is your container having solution of density, okay, and this be your solution. Okay, now what? As I have explained to you that this be your suppose the air bubble, and the air bubble is moving steadily in upward direction according to question, rising, so it means it is moving in upward direction. It means the thing is quite similar, that if we have a body and the body is passing through or flowing in a fluid or passing through a fluid, it means that it is quite easy that a dragging force must be there. The dragging force, the formula, that is 6 pi eta rv, and this formula is given by the formula or we can say the law, that is your Stokes law. Now what? As we can see here that the air bubble is rising up. Because it is rising up, it means there must be a buoyant force, because with the help of buoyant force only one can move upward. Okay, so here must be a buoyant force, let be that will be FB. B stands for buoyant, and we know that the buoyant force is equal to the weight of the fluid displaced, weight of the fluid displaced by the body. Okay, so weight means mg is the weight. Now one thing you should remember, that here m stands for the fluid, mass of the fluid. Okay, not for mass of the body. So if we write mass, then we can simply say that we have a formula, that density equal mass upon volume. So mass equal density into volume into G. So FB, buoyant force. Okay, and we have one force F, that is the dragging force, and dragging force will be in downward direction, and the bubble is rising up, so buoyant force FV will be in the upward direction. So I hope and believe that up to here each and everything is clear now. So the resultant force we have, and what is the resultant force? So the resultant force as we believe that in this container the air bubble is moving upward, it means FB must be greater with compared to the dragging force. So the resultant force will be FB minus F. Okay, this is the resultant force, and according to Newton's law, Newton's second law of motion, the resultant force is always equal to mass into acceleration. Now one thing is very clear, that it is given the question that it rises steadily. Steadily means with a constant speed, and if the speed is constant, it means change in velocity is 0, and if the change in velocity is 0, then acceleration will be 0, and if the acceleration is 0, then we put the value of air, and we finally get that FV minus F will be 0, and that is only for the steady rise. Okay, constant rise, constant speed. So we have F, that is equal to FB, the value of F, that is 6 pi eta RV, the value of FB, and the value of FB, that is rho V into G. So it is rho, that is V into G. Now this V is your volume, remember that this is your volume and this V is your speed. So don't be confused. Now in place of volume, we can easily write down the volume of the sphere, that is 4 by 3 pi r cube. This is the volume into G, and this is 6 pi eta r V. Now we have to solve this, and then we will get the required result what we want. We have to calculate the value of eta. So we can easily write that firstly we will take another slide for you, and then we will write that 6 pi eta RV. So 6 pi eta RV, and that will be equal to rho times 4 by 3, rho times 4 by 3 pi r cube times G. Okay, now what? We will cancel out something. As you can see, r, and that will be only, there will be power 2 remains. It is 4, so 2 2 ja 4, and it is 2 3 ja 6. Okay. So we have 3 pi eta into v, and it is rho into 2 by 3 pi r square into g. So up to here each and everything is clear. Now pi to pi cancel out, quite easy, and we have to find the value of eta, so it will be rho into 2 by 3 into r square into g, and divided by 1 by 3v, because that is 3, that is v, so it will become on the other side. Okay, now put the value what we get. So we have the values of the density 1750. So put the value 1750 into 2 by 3 into r. So where is r? R diameter is 2 millimeter, so r will be half, it means 1 millimeter. So put the value of r, that is 1 millimeter, so 10 to the power minus 3, and the square of it. Now g, the value of g is given here or not? It is not given, so we will take 9.8. So it will be 9.8 the value of g into 1 divided by 3 into v, and v means speed. Speed is given 0.35 centimeter second inverse, 0.35. So 0.35 centimeters, so 10 to the power minus 2. So it will be meter second inverse. I hope that up to here each and everything is clear to all of you. Okay, now what? We will simply calculate it, and we get the result, we get the answer. So what we get the answer? Eta equal 11 and twice. So this is your answer, this is your result, and I hope that this numerical as well as the derivation is clear to all of you. So try to solve the questions by yourself. As much as numericals you will solve, the same you will be benefited in the concept. So we will meet in the next lecture for we can say that please try to understand each and everything, just memorize it, just try to frame each and everything in your mind if you really want to learn the physics. And that things I have continuously repeated so many times. So thanks for watching me, thanks for listening me, best of luck.